what can we truly learn within hours when an interstellar comet brushes past Mars and then slides behind the Sun? On Oct 3, 2025, around 040 UTC, 3I Atlas made its closest approach to Mars, roughly 0.19 AU, about 2830 million kilometer, from the planet, a geometry rare enough to place a fleet of Mars orbiters and ground observers on alert. For a brief window, the red planet and its spacecraft could watch a visitor that does not share the Sun's history. 3I Atlas arrived on a hyperbolic interstellar path and is now accelerating toward perihelion in late October 2025. NASA projects perihelion near Oct 2930 at 1.4 AU, just inside Mars's orbit. From Earth, the comet sinks into solar conjunction for much of October, leaving only narrow opportunities before and after. That constraint, hours, not weeks, focuses our plan. The simplest, highest value measurements are also the fastest to repeat. Time series photometry to trace brightness changes, 2 or 3 color curves to sense dust gas balance, and coma-shaped snapshots to catch short jets or a subtle sunward spike. A rotating nucleus modulates sunlight scattered by dust. Intermittent jets add flicker and asymmetry. If rotation is slow and dominated by one active area, we expect a gentle, repeatable wave in the light curve over 1 to 2 cycles within a night. If multiple vents compete, short timescale kinks should appear. Mars orbiters extend this test. ESA's trace. Gas Orbiter has already demonstrated it can detect the fuzzy glow of 3I Atlas from Mars orbit, stacking short exposures to reveal the Coma event. That proof means brief. Repeated sequences can sample morphology, while Earth-based telescopes, when geometry allows, record synchronized light curves. Together, they can bracket rotation and flag transient jets. Why race now? Because the comet's Earth view is closing. Event. Through October, 3I Atlas as Flyby slips behind the Sun as seen from Earth and then reappears rapidly after perihelion. Any pre-conjunction data help anchor models of its spin state and outgassing before geometry changes. With dense time series in this window, we can constrain not only period and jet behavior, but also search for tiny non-gravitational acceleration, minute trajectory shifts caused by asymmetric outflow. If those shifts correlate with brightness and coma asymmetry, the case strengthens that outgassing, not unknown forces, drives the deviation. So our promise is modest and testable. In just a few well-planned hours, we will extract 3 things: an initial rotation constraint, evidence for or against narrow jets, and the first clues to any non-gravitational acceleration, using only brightness, color, and morphology, tied to precise times around the Mars flyby and the lead-up to late October perihelion. Then, when the comet emerges again, we will check those predictions against fresh data. The clock started with the Mars encounter. On Friday, October 3rd, 2025, 3I Atlas passed roughly 29 to 30 million kilometers, about 18 million miles from Mars, placing ESA's orbiters in a favorable vantage to image a compact coma as Earth slid toward poor geometry. ESA reports both ExoMars TGO with CASs and Mars Express acquired sequences between Oct 17. The next anchor is perihelion in late October. NASA lists the closest to Sun passage around Oct 2930 at the 1.4 AU, just inside Mars's orbit. Around Oct 21, Earth-Comet solar conjunction minimizes elongation, making ground follow-up difficult until early December when elongation improves. Instruments define what we can learn in hours. JWST's NIR spec has already delivered a compositional baseline, a CO2-dominated gas coma at 3.3 AU inbound, with CO2, H2O8, and sunward-enhanced outgassing, evidence that CO2, not water, drives early activity in this interstellar visitor. If CO2 sublimation dominates, torque and brightness fluctuations can decouple from the standard water-driven daily cycle seen in many comets. From the ground, the VLT fact pack adds timing. X-Shooter and UVES detected numerous neutral nickel lines, while iron was absent or far weaker at larger distances. CN emission turned on later, mid-August, with production ramping as the comet approached the Sun. This sequence, Ni early, CN later, pins down activation thresholds, nickel-bearing volatiles, EBSEG, that carbonyl compounds could release at lower temperatures than HCN, producing nickel without iron when heating is still modest. Color and shape carry geometry. Reports of a subtle sunward spike, an anti-tail, are consistent with viewing the dust sheet edge-on when the line of sight nears the comet's orbital plane. Large grains linger in the orbital plane and can project sunward from our perspective, while the ion tail still points anti-solar. Near conjunction, brief windows from Mars or space assets should favor detection of a short, narrow spike aligned with the projected orbital plane. Why this matters for rotation and tiny accelerations. Asymmetric gas release imparts a rocket-like push, altering the orbit by milliarc seconds over days. Dense, time-stamped photometry and morphology, especially when synchronized with Mars-side imaging, lets orbit fitters correlate brightness, Coma asymmetry with residuals from a gravity-only trajectory. If outgassing is strongly one-sided, we expect a coherent non-gravitational signal that grows through perihelion and tracks activity proxies. Practical numbers to steer campaigns. Nucleus size remains uncertain, but Hubble-based estimates place it between a few hundred meters and several kilometers, guiding exposure choices. Mars orbiter images confirm the Coma's detectability even when Earth view is constrained. JWST may attempt post-perihelion looks starting Novi 2, extending the timeline as the comet re-emerges from the Sun. The most rapid composition changes should cluster between late October and mid-November, when heating peaks yet geometry begins to improve. Taken together, the timeline: Octi 3 Mars, Octi 29 to 30 perihelion, early December return. The instrument suite: JWST and IR spec, VLT X-Shooter, UVS, ESA Mars orbiters. And the spectral sequence: CO2-rich gas, late CN onset, NIFA 1 wing early, define exactly what to collect in hours. Synchronized light curves, 2-color indices, and morphology snapshots keyed to the geometry. These facts seed the tests we will run next. We now place 3 clear, testable ideas on the table and ask them to compete against the same hours-long datasets we can gather around OC3 2025 near Mars and through late October perihelion, HH1, single subsolar jet with a slow spin. One dominant vent near the subsolar region releases CO2-rich gas and dust. As the nucleus rotates slowly, the jet direction sweeps only modestly, producing a smooth, near-sinusoidal light curve. Support comes from an early CO2-dominated coma and nickel without iron, both consistent with low-temperature volatiles driving activity before water fully engages. A faint, narrow sunward spike, anti-tail, seen when the orbital plane is edge-on, could align with a stable dust sheet fed by a steady jet. Weakness: late CN onset and any reported short timescale flicker would argue against a single placid source. In 2 to 4 hours of time series photometry, color indices, BV, VR, drift smoothly with brightness, and repeated coma snapshots show the same asymmetric lobe. Astrometric residuals accumulate with one direction preference that persists past perihelion. H2, multi-vent activity with a rapid or tumbling rotation. Several vents open at different latitudes. Non-principal axis rotation, tumbling, or a short period mixes jet orientations, creating light curves with kinks and amplitude changes. Support: intermittent CN surges or step-like color shifts near October 3, and late October would fit bursts from different vents. The anti-tail could be episodically enhanced if larger grains are emitted in pulses. Weakness. If spectra and colors remain remarkably steady and the Coma lobe geometry is repeatable, H2 loses ground. Within hours, we record uneven light curve segments, brief brightening followed by a plateau, and morphology frames show the brightest feature rotating or relocating by noticeable angles. Residuals in orbit fits change sign over adjacent nights, consistent with thrust vectors that do not average to a single direction. H3. Nearly isotropic CO2 outgassing with dust sheet geometry effects. Outflow is close to spherical, but viewing geometry and grain dynamics produce the apparent sunward spike. Support, weak photometric modulation, stable colors, and a coma that looks symmetric except for a thin spike near the orbital plane. Nickel lines without iron arise from uniformly escaping low-temperature carriers, not localized vents. Weakness. Any strong periodicity or jet-like corkscrew would contradict isotropy. During short pre-conjunction windows, and again just after the late October perihelion, the light curve remains low amplitude and repeatable. The anti-tail's position angle tracks the projected orbital plane, not the nucleus rotation phase. Non-gravitational acceleration solutions remain small and steady, scaling smoothly with the total activity proxy. How to adjudicate quickly. Pair dense photometry with synchronized two-color measurements and a few high SN images spaced tens of minutes apart. If H1 is right, we'll see coherence, a repeating wave, a persistent lobe, and steady direction residuals. If H2 is right, the curves will be irregular within a night, and morphology will shift measurably. If H3 is right, colors and brightness stay quiet while the spike locks to geometry. The reappearance in early December offers a clean check. The favored pattern should resume under new phase angles, letting us confirm or falsify the winning hypothesis with fresh light curves and updated orbit fits. Here is a calm, realistic plan for observers. Begin with time series photometry. Choose a steady cadence, one exposure every 2.4 minutes, and hold it for 2 to 3 hours. Keep the field fixed, avoid filter changes mid-run, and record accurate UTC start-stop times. Use bias/dark, flat calibration, plate solve each frame, and select 2 or 3 comparison stars of similar color from a modern catalog. Keep them unsaturated and stable through the sequence. For compact Coma, small photometric apertures, about 2 with a clean sky annulus, preserve sensitivity to short-term changes. Slight to focus on bright comparison stars can reduce scintillation. To add color, run a short BVR cycle before and after the main sequence, or on a second night, so the light curve stays homogeneous. If you own a Comet CN filter near 388 and Wenyan, try brief series of stacked images. Even a weak detection helps separate gas from dust. Expect CN to be faint and uneven. Log every parameter so others can cross-check. Morphology is a second independent channel. Capture a handful of high SN frames spaced tens of minutes apart, then stack twice. Once on the stars, for context, and once on the comet to freeze the coma. Compare radial profiles sunward versus anti-sunward, measure the position angle of any thin spike, and note whether it matches the projected orbital plane. A simple PSF subtraction, if your stars are tight, can reveal jets or a delicate anti-tail. If you can measure positions precisely, add astrometry. Short exposures to limit trailing, plate solve with a recent Gaia catalog, and report uncertainties honestly. When combined with global light curves and morphology notes, small residual patterns can support or challenge non-gravitational terms. Windows to watch. brief gaps before late October perihelion, then the post-conjunction reappearance in early December as elongation improves. 3 takeaways. Rapid, careful light curves constrain rotation. A few clean images map jets and any sunward spike. Synchronized timing across longitudes lets tiny accelerations stand out. If you capture anything, share a calibrated frame, your method, and the exact times. Your quiet 2 hours may be the data point that decides between our 3 hypotheses. We set out with a modest, testable aim to use hours, not weeks, around the Oki 3, 2025 Mars flyby, and the late October perihelion to extract 3 clues about 3I Atlas, its rotation, its jets, and any non-gravitational acceleration. In Part 1, we framed the constraint. The comet brushes Mars and then sinks towards solar conjunction. So fast, repeatable measurements are the highest value. The promise was simple: time series brightness, brief color checks, and a few morphology snapshots can already outline a rotation period, reveal narrow activity, and hint at asymmetric thrust. Part 2 delivered the fact pack and observing geometry, a CO2-dominated coma, the later onset of CN, the early appearance of nickel lines without comparable iron, a near-ecliptic path that can project a sunward spike when seen edge-on, a late October perihelion near about 1.4 AU, and a likely reappearance in early December as elongation improves. Those facts tell us which instruments matter in hours: synchronized photometry, 2-color indices, and morphology frames that can be repeated swiftly by both professionals and advanced amateurs, plus opportunistic views from Mars orbit. In Part 3, we posed 3 competing falsifiable hypotheses: H1, a single subsolar jet with slow spin; H2, multivent activity with rapid or tumbling rotation; and H3, nearly isotropic CO2 outgassing with geometry-driven appearances. Each came with predicted light curve behavior, color stability, morphology patterns, and how non-gravitational residuals should evolve. Part 4 translated this into a field plan: steady cadence photometry, careful calibration, small apertures for compact Coma, short color sets, occasional CN filtering, comet-registered stacks for morphology, position angle tracking for any anti-tail, and honest astrometry to feed orbit fits. The closing invitation is practical. Share your times, methods, and calibrated frames. With many quiet, well-timed hours stitched together globally, we can choose the best hypothesis now and test it again after the comet returns to view.